All right, so we saw this problem, I think, on the practice questions or for the kinetics test, or possibly during lecture, I can't remember. And the question was, what is the activation energy of the forward reaction, right? And so what was the answer for that question? Yeah, it's B. So the forward reaction is saying that these are the reactants and these are the products, okay? And we're progressing, not on time, but in the progress of the reaction from a state, particular potential energy level of the chemical bonds, going over the activation energy hump, where there's some transition state here, and then dropping down to the energy of the products. Is this an exothermic or endothermic reaction? My reactants are starting with an energy level. My products are at a lower energy level. It's exothermic. Yeah. Oh, I thought you said endo. I'm sorry. I misheard. That's my bad. Yeah. No, okay. Right. We're all good. I was like, oh no. Yeah, energy is released. Right. That energy, the amount of energy A is released. Yeah. But if you were wondering why it specifically said the forward reaction, that's because many chemical reactions are reversible. And so what would the activation energy of the reverse reaction be? Say it louder. C, yeah. So if this is our reactants and these are our products, then we have a much larger hump to get over because we still have to reach that same energy level of the transition state, and then also we're going to end up with a higher amount of energy overall. All right, so we can talk about these energy diagrams as if we were looking at reversible reactions. And typically, we're still going to, when we have reversible reactions, we're still going to write the reactants as on the left side, and we're going to call what's here the reactants for the forward reaction and the products for the forward reaction. We're going to talk about things generally in terms of the forward reaction, so it will be similar to what we've said before. But just recognize that the reaction can go backwards as well. So we've talked as if our chemical reactions are going to completion. All of our stoichiometry problems are assuming that the reaction is going to go to completion, right? That we're going to, however much we put in is how much we're going to get out, et cetera. Unless we have, at least for our limiting reagent. And when we have that, we use the one-way arrow, which we've been using all along, to indicate the transition from reactants to products. But a lot of our reactions don't go to completion and are therefore reversible. So this is an example that's being shown in this schematic here. Hydrogen and iodine combining to form hydrogen iodide or hydroiodic acid. This is a reversible reaction. We draw the arrow going in both directions. You can draw it like this, or you can draw two arrows like that. It doesn't really matter as long as you have arrows pointing in both directions, but this is sort of the standard way, like a half arrow pointing forward and a half arrow pointing in reverse. This is what you'll see in a textbook. I would suggest just writing it this way. But like if you wrote it like this, you would not get points taken off. Okay. So if we think about our rate of reaction, we talked about, this is a graph of concentration over time. So this is a rate graph where we're looking at the concentration of, is the red line going to be the concentration of reactants or the concentration of products? Right, products, because we're starting at 0, right? And we're going up to a certain amount, a certain concentration of our product. And the blue line would be our reactant. So we're starting with a certain amount of reactant, and that's going to go down. And we talked about how we get to this point where we reach an asymptote, where it plateaus off. And for reversible reactions, the reactants and the products are both going to plateau but they're definitely, the reactants are not going to get to zero because there's always going to be a little bit of the reverse reaction going on, even if the forward reaction is super strong, okay? So when we reach equilibrium, what that means is that the rate of the forward reaction still happening in the beaker or whatever is the same as the rate of the reverse reaction. So one thing is turning into another at the same rate that the products are turning back into the reactants. So the overall concentrations are constant, all right? So we're changing a tiny little bit, but we're changing a tiny little bit in both directions. So when we see the graph, the concentration graph, reaching that plateau, that is where we consider it to be at equilibrium. But it's dynamic. It's not a static equilibrium. It's not like the reaction is done, complete, and not happening anymore. It is still happening on a micro scale, but in both directions at the same rate. Okay. What is important, and this will be sort of the second part of this unit, is that we can control where that equilibrium happens by changing conditions. And if you took Honors Chem last year, you may vaguely remember this stuff, but we'll be going into it in a little bit more depth. So a few things that have to be true for equilibrium. So when we're at equilibrium, the forward and reverse reactions are the same rate. The concentrations of reactants and products are constant. We have to have a closed system. So we haven't talked so much about closed, open, and isolated systems this year. But an open system is one where stuff can get in and out. Anything can get in and out. Mass can get in and out, and energy can get in and out. So this is this electrolysis reaction that's going on right here. We're electrolyzing water into hydrogen and oxygen. This is an open system because I can change the temperature pretty easily, but just by changing the temperature of the room. Some of the water can evaporate. So this is considered an open system. I can gain or lose mass. I can gain or lose energy. Okay. A closed system would be one in which you can't, mass cannot move in or out. Okay. Okay. So in order to have equilibrium, we have to have a closed system. We can't just have a system at equilibrium when the water here can evaporate. It's not going to be at an equilibrium point. Also, we're adding energy, but that's another story. All right, that's opposed to an isolated system where neither matter nor energy can move in or out. So that would be something like your Yeti cup, okay, would be considered as close to an isolated system as we can get to, right? Really, really good thermos with the lid on and closed, okay? And then we generally, when we're at equilibrium, we don't see changes. We don't see levels of solution fluctuating. We don't see amounts of precipitate being added or disappearing. We don't see color changes. But there are those microscopic, those atomic level, molecular level changes happening at a very, very small rate. So that's why we call this dynamic equilibrium, because it is constantly changing even when we are at equilibrium, okay? So this, I'm going to flip some of the pages on your study guide a little bit. So this is on page 4, skipping over a little bit. We'll come back to what we skip over in a second. So this is a typical graph where rather than the concentrations that we were looking at here, where we're seeing the concentrations of the products go up and the reactants go down, this is a graph of the rate of reaction, okay, over time. So how fast is the reaction going? That will change over time until we reach an equilibrium. So at the beginning, the rate of the forward reaction is going to be highest and the rate of the reverse reaction is going to be 0, because all we have are the reactants that we put in. We don't have any of the products yet to turn back into reactants. Okay? But that forward reaction, as it continues, we're going to start running out of reactants. The concentration is going to change. That's going to change the rate of reaction, as we learned about last chapter. And so eventually, that rate is going to decline and hit a plateau. And the rate of the reverse reaction, as we make products, some of those products can then react to make the reactants in the reverse reaction. So the more products we have, the faster our reverse reaction is going to be. And then at some point, we reach the point where the rates of the forward and reverse reactions are the same. So I want you to be able to recognize when you have a rate of reaction graph where equilibrium is where the lines meet versus a concentration graph where equilibrium is where the lines are constant. Okay? Okay. So this is that reaction we were just talking about, the hydrogen and the iodine combining to form HI. And this is an example of how if we started with 5 moles of hydrogen and 5 moles of iodine, our concentration of reactants would be 10 moles per liter, because this is a 1 liter vessel. So our concentration of reactants would start at 10 and our concentration of products would start at 0. And then we could actually watch this reaction happen and measure the concentration over time and therefore see the point at which equilibrium has been reached, where both concentrations are constant. Again, there's still a reaction happening here in both directions at a very small number of particles. So the overall concentration is the same because the reaction is happening equally in both directions. Okay, so I talked about, I should probably just reorder these slides to go better with the study guide and with the list of things. But when we talk about a closed system, again, we're talking about one where matter can't escape from the reaction bus, neither the reactants nor the products. Now, a great example of this is just a flask full of water. Now, this isn't a chemical reaction that happens when water evaporates. It's a physical process, right? Change in state. But when we first put the cap on, there's going to be a certain, pour the water in, put the cap on, a certain amount of the water particles are going to start evaporating. And so that process is going to go, going from liquid to gas would be our forward reaction, and that's going to start happening more and more and more until we get enough gas particles where some of them are going to condense back into liquid. And then we're going to have the reverse process. Yes? Can you say that again? Kind of. It's kind of like that. So that you have something similar with evaporation or vaporization, but this is going to be dependent on the concentration in the air above. So the extent to which we get evaporation here depends on the vapor pressure, which is a physical property of the substance. But yes, the same idea is there. Some number of them are going to randomly have a high enough kinetic energy to break the intermolecular forces that are also at the surface and can be released into a gas, right? So that determines the rate of evaporation, and then the size and concentration of the air, air or gas, whatever surrounding the liquid is going to determine, and the vapor pressure of the substance is going to determine where that equilibrium is reached. So that is considered to be physical equilibrium. So again, that's a process, a physical process going from liquid to gas and gas to liquid. It's a change of state. It's not a chemical reaction, so we consider that to be physical equilibrium versus chemical equilibrium that involves an actual reaction. However, we can write a reaction statement for this, just keeping the states of matter. So our liquid water is turning into water vapor, but that's a reversible process. And we can talk about the rate at which that process happens relative to the concentrations, et cetera. Okay. So again, we're not reacting anything here. The water is still water. It's just changing its state. And once we reach that state, we're not going to be able, even though there are still water molecules evaporating, water molecules condensing, we're not going to be able to see a difference in the level of the water, right? Because those reactions are going to be happening, those physical processes of evaporation and condensation are going to be happening at the same rate. So we won't see any effect on the overall level of the water. Okay, so that was kind of going back to the page 3 on your study guide talks about the physical equilibrium and about the idea of that closed system. And then you can, the exercises on page 3, if you want to, you can go through, not right now, and write out examples of equilibrium reactions for those processes. Okay. Okay, so how do we talk about equilibrium? How do we measure when equilibrium happens? What direction is going to be favored in a reaction, to the forward versus the reverse, et cetera? So what we're going to use is this thing called the equilibrium constant, or capital K sub C, subscript C. So constants are generally K, but this particular equilibrium constant, we'll see when we do acids and bases. We're going to take this into acids and bases and see it a little bit specifically for the rates of dissociation of acids and bases, but same concept. So if we look at, oh, that's interesting. I guess my pen was close enough. If we look at this generalized reaction, so we've got, and we're now on page 6 of your study guide. So if we look at this general reaction, we've got little a, little b, big B, et cetera. The small letters, the lowercase letters are coefficients. And the large uppercase letters are substances. And we're writing this as if we have 2 reactants and 2 products. Obviously, that's not always the case, but just for a generic intro to this, that's a reasonable way to write the reaction. So this is a sort of a generic reaction with generic coefficients. And we're going to write what we call the equilibrium expression, or the equilibrium constant expression for this reaction. And this is how it's written. So your K sub C is going to be equal to your product concentrations raised to the power of the coefficient over the reactant concentrations raised to the power of their individual coefficients. So this is the general equilibrium constant expression. I actually like, and I think your study guide does this, actually writes this as with the square brackets, which means concentration. It doesn't, the issue is, the reason it's not written like this here is because we don't always measure concentration as our example of rate. Yeah. I'm going to do an example right now. Yeah. And then the reason this is K sub C is that we're specifically, this is talking about concentration. There are other K subs, like if we're using pressure instead, it would be K sub P. So if we go back to that hydrogen iodine reaction, we can write an equilibrium expression for this in general. So let's do that first. So our K sub C for this would be the concentration of our products. We only have one product, that's our HI. And we're going to raise that to the power of the coefficient. And we're going to put that over the concentration of our reactants. So the concentration of H2 raised to the first power times the concentration of I2 raised to the first power, which is just itself, right? You don't have to. No, you don't have to. It's up to you whether you want to. It's not wrong to write it. It's not wrong to not write it if it's a 1, okay? I like to write it because it reminds me that I've actually looked at the coefficients and as opposed to just leaving it alone. Okay, so now that we've written this, you can write this for any reaction, and that's a thing that commonly comes up as part of paper 2 is write the equilibrium expression for this reaction, right? So that should be pretty, you just use the general formula. However many products you have get multiplied together here, however many reactants you have get multiplied together down here. But now that we have this, we can actually calculate the value of this equilibrium constant, okay? So we can just plug in the numbers. So we can say the concentrations of the H2 and the I2 were 0.0037 moles per liter and 0.028 moles per liter for the product. So we can just throw that in. We can say 0.028 to the second over 0.037 to the first times 0.037. Okay, and that then, calculating that will give us our equilibrium constant for this reaction that's described in the question. Notice that if our concentrations change, the equilibrium constant changes, okay? So the equilibrium constant is not something that's constant for this reaction no matter the conditions. Yeah? Oh, you're right, it's 0.037. Thank you. Thank you for checking. Yep. Yep, no, you're right. So, 0.028, and there's my squared. Divided by 0.007. So tell me if I punch this in correctly. I get 57. Well, technically we only have 2 significant digits. So I would say that the KC is 57. If you took it out a little further, maybe 57.27, something like that. Is that what you guys got? Okay. So generally constants, this kind of equilibrium constant isn't going to have units, okay? There's no unit to this. So I think, okay, so why do we care about this constant? What does it tell us? Well, again, it's going to be dependent on the conditions. In this case, this is a concentration dependent constant, and so it's dependent on the relative concentrations of the reactants and the products that we start with. Okay, not that we start with, at equilibrium. So if we put these things together, this is the concentration we should get at equilibrium. That's for this particular setup. So if we calculate Kc, that can tell us something about which direction the reaction is primarily going in. Right? Did the reaction shift in order to get to equilibrium? Did we shift this way or did we shift this way? Okay. So your study guide starts talking about this on page 8. So depending on sorry. Yep. It doesn't have units. Yeah, it's just a number. Yep. So the value of this is going to tell us how far we've gone to completion from the original reactants when we reach equilibrium. Okay? So if we have a high Kc, then that means that if our Kc is significantly higher than 1, then that means that most of our reactants have been converted to products. We've gone almost all the way to a complete reaction. Okay? That would be something like this reaction, where we've almost converted all of our reactants. We don't have very much left. We've converted a lot into our products. That would be a high Kc. And then if the Kc is low, if it's significantly less than 1, then that's going to indicate that the forward reaction isn't going anywhere, and the reverse reaction is dominant under these conditions. Okay, under these concentrations, the reverse reaction is going to dominate, and only a little bit of the reactants will become products. And this is all, notice, at a particular temperature. So the equilibrium constant, again, it's not really a constant because we're talking about a dynamic system. It's dependent, in this case, on the concentration. It's dependent on the temperature. So the reason we would want to calculate Kc for a reaction would be to tell us at equilibrium, are we going to have more products? Are we going to have more reactants? So if our Kc is equal to 1, that means the concentrations of our reactants and products are exactly the same. And so generally that's not where our equilibriums lie. They don't generally lie exactly at the center. So again, if we have something like a Kc of 100, we're going to have a lot more products than we have reactants. If we have something on the lines of 100th, less than 1, we're going to have a lot more reactants still in the mix at equilibrium than products. And if it's significantly less than 1, then it basically means we've hardly done the forward reaction at all. If it's significantly, like orders of magnitude greater than 1, then it means we've practically gone to completion. So just being able to remember what direction a high Kc is, lots of products that we're sending our reversible reaction to the right. Okay? So the reaction is shifting to the right to reach equilibrium in the case of a high Kc. In the case of a low Kc, the reaction is shifting to the left to reach equilibrium. Right, I think I want to, yeah, okay, we'll just go over this, and then I'm going to stop and have you do a couple of the problems in your study guide. So typically, we talk about the reactants being on the left side and the products being on the right side. So our A plus B, B plus D, consider A and B are reactants and C and D are products, even though the reaction might actually shift in either direction to reach equilibrium. But we still talk about A and B as our reactants and C and D as our products. And when we write our Kc, we write it that way, with the products on the top, concentrations of the products on the top, and the concentrations of the reactants on the bottom. But if we reverse the equation, if we write the equation backwards, then the value is going to be the reciprocal of that. It's going to be 1 over that. So if you think about our original generic formula, that should be at lowercase d. If these are our products and these are reactants, that's how we're going to calculate it. If we flip these, that's the same as saying 1 over the Kc, right? So if we write the reaction, this particular reaction this way, here's our Kc at this particular temperature. If we write it in the reverse, then we take this, we take 1 over this to get our Kc. Okay? At the same temperature, again. This is something that gets into a lot more depth in the AP curriculum than in the IB-SL curriculum. But obviously, the other things that we can do to change the equilibrium constant, we can change the concentrations. We can also change we're essentially changing the concentrations by changing the amounts, right? So that's essentially because if we change the coefficients of the reaction, then we are essentially squaring or square rooting the equation or the setup for the Kc. And what's that? Then it squares. Yeah. All right, I think I'm going to stop here because the next set of stuff is going to get more into Le Chatelier's principle and how we can, what factors affect where the equilibrium lies. And that is the bulk of the kinds of questions that they'll ask you about. So I want to kind of start that fresh next week. So in your study guide, I would do a couple of the exercises on page 6. So writing the equilibrium expressions just to get comfortable doing that. I'm sorry, what? Oh, yeah. Yeah, absolutely.